Hi everyone, I'm going to introduce dilution in this video, which is the second topic in section 8.1. We've already talked about molarity a little bit, and this is kind of a twist on that topic. One thing I wanted to do to begin was to go over the assignment which was due. By the time you watch this video, it will have already been due, and that's the molarity assignment, which was due on Monday, the 30th. So real quick, I want to show you the solutions to that and make sure there's understanding there. My suggestion was that you show your work on paper which you hold on to so that we can review it here, and of course you were only typing in your final answer to these calculations in the assignment in Google Classroom, but hopefully you saved your work so you can look back here. For the first two questions, you would need to get the formula of the compound right in order to get the molar mass right, if that makes sense. So calcium sulfide, of course, calcium is a +2 cation, sulfur is a -1 anion, so in order to get 72.14 as the molar mass, you'll need to have that formula right. Notice that when we use this formula, N equals mV or M equals N over V, the number of moles, N, must be in moles, not grams. So I've done a conversion here. And then I've divided by the volume in liters. The volume must be in liters. And really, this says volume of solvent. It should say volume of solution as a technical definition, although usually we ignore the negligible volume that the solute typically contributes, and we assume that the volume of solution and the volume of solvent are the same. In the second question, we're talking about sodium sulfate, and sodium is a +1 cation, sulfate's -2, so again, got to get that formula right to get the molar mass right. Calculating the molarity is simply number of moles divided by volume in liters. The next one, we're solving for number of moles, and the formula N equals mV can be used. The volume's 1 liter, so the number of moles is equal to the molarity, right, numerically. It's funny how the rules of significant figures don't really apply here, because if I ask you to make 1 liter of 0.25 molar solution, then of course you want to make exactly 1 liter of exactly 0.25 molar solution. So it doesn't really make sense to round this to a smaller number of significant figures. If you have an instrument that can give you the number of moles even more precisely than 2 significant figures, great. So the rules for significant figures don't really apply when we are trying to calculate an amount that is sort of an ideal we're shooting for. We want to be as precise as possible. We're not limited by a measurement. So remember that significant figures really are another way of saying a measured number or a measured digit. How many grams do I want to use? Well, if I use 3 significant figures, you can see I converted this number of moles to grams. Then I would measure out 10.6 grams. But if I have a balance that can measure out the exact mass, 10.5985, that would be a very expensive balance, but that would be even more precise. So here we're not limited by a measurement in terms of how many significant figures we should use. We can include as many significant figures as are reasonable. So a lot of these questions I'm going to ask you to put in a certain number of significant figures, since we're not necessarily limited by a measurement. In this question I asked for 3 significant figures. In the last one I asked for 5 significant figures. So there's no reason to round to 2 significant figures here. If you want to make 3 molar solution, might as well make it exactly 3 molar. We want to make 1/4 of a liter. And remember, in order to use the molarity equation, all volumes must be in liters. So here I've converted moles to grams, divided by liters, and I've got a final answer which is in grams of sodium chloride. So let me know if there's questions about this assignment, and then we'll go on to talk about the new content next, which is dilution practice. Alright, so let's take a look at the PowerPoint slides which correspond to these new sets of notes. The notes are online, either as PDF or PowerPoint, so if you want to look at just the slides without the video, then certainly you can do that, and these are the same slides that are posted there. First of all, we talked about what a stock solution was in the last video. A stock solution is simply a routinely used solution in concentrated form. So for instance, when I need to buy hydrochloric acid for our labs, I purchase it as 12 molar hydrochloric acid, very concentrated, and that reduces shipping costs and is convenient, but we'll then dilute those solutions down. So these are dangerously concentrated acids. Sulfuric acid is typically purchased as 18 molar sulfuric acid and hydrochloric as 12 molar. And then we take a certain amount of the stock solution, some small initial volume, and add water. More technically, we actually add acid to the water, but we dilute the solution in that way. So dilution is what we're introducing here, and it essentially means watering down. The concentration of a solution is lessened. And in order to dilute a solution, you add more solvent. And almost always our solvent is going to be water. Here, if you look at this little drawing here, you'll see that water is indicated there, and you can see the water molecules. You'll recognize those. And this is representing hydrochloric acid. Before dilution and after dilution. Notice before dilution there are 1, 2, 3, 4 of those molecules of hydrochloric acid depicted. So let's say that represents 4 moles. After dilution there are still 1, 2, 3, 4 moles. Well, of course, we only added water, so we're adding solvent, but the number of moles of solute doesn't change. And that's an important idea. The number of moles of solute before the dilution is equal to the number of moles of solute after the dilution. And you remember the symbol for moles of solute is a lowercase letter n. So we could say n initial equals n final. And this is the beginning of our calculation for dilution. Remembering that during the process of dilution, the number of moles does not change, and that really what changes is the volume and, of course, the molarity, since we know n is equal to mv from our previous work. So if n initial equals n final and n equals mv, then mv initial equals mv final, or mivi equals mfvf, where mi is the initial concentration and vi is the initial volume. Initial refers to the stock solution, in other words, the concentrated solution we begin with. And MF and VF are the final concentration and the final volume. They are dilute. Notice that MI will always be a greater number than MF because we are diluting the solution. But VF will always be a greater volume than VI because the more solvent we add, the more solution we end up with. So we're going to walk through a couple of practice problems that are in the PowerPoint, and I'd encourage you to pause the video and give it a shot before watching the whole solution that I'll demonstrate. So the problems I'm going to walk through here are also in the PowerPoint that's online, so you can look at those slides. I'm going to go to the document camera so I can show you how I'd solve them by writing out the solution. We're going to make a shopping list of variables and write the formula we're going to use, like we learned before when we were doing like Q equals M delta TC kind of problems. What is the concentration of a solution that's prepared by diluting 25 mils of 6 molar acid to a total volume of 50 mils? So it's asking for concentration, which means the molarity is what's unknown, but which molarity is unknown? Final or initial? The final concentration that results from this dilution is what we're solving for. What's that new concentration? Notice the initial concentration, Mi, is 6 molar. So again, make a list of variables, identifying which one's the unknown variable. The initial volume is always going to be the smaller volume. So in this case, that's 25 mils, and the final volume here is 50 mils. Now, notice in the last lecture, I told you that this molarity formula really only works if we're in liters. However, in this new formula, we can, if we're careful to pay attention of unit cancellation, avoid converting everything to liters. So for instance here, I want to take the equation which I just introduced, MIVI equals MFVF, and I want to solve for MF. Of course, I can solve for MF if I divide both sides by the quantity VF, and I'm left with the equation that I'm going to use here. Final molarity is MIVI over VF. And sometimes you'll see this written as M1V1 equals M2V2, but of course those are equivalent. Now I can go ahead and solve for molarity. And notice when I solve for molarity here, I've got a volume in milliliters and a volume in milliliters. Milliliters will cancel, and I'll be left with a molarity. if I had converted both of these to liters, which you're welcome to do, remember this would be 0.025 liters and this would be 0.05 liters, then I'd have volume in liters and a volume in liters, which would cancel, and I'd still be left with molarity. So in this form of the equation, we can avoid converting to liters as long as you're careful that units actually cancel out, and I'll show you some other examples of that soon. But it certainly never hurts to put everything in liters, and that's maybe a good rule of thumb to keep things simple. So MIVI is going to be 6 multiplied by 25, and I'm going to go ahead and keep in milliliters this time, and then I'm going to take that product and I'm going to divide by the final volume, 50, and it makes sense that if I want to double the volume, then I'm going to have the concentration, and I'll go ahead and report that to 3 significant figures. The new molarity is 3 molar. Let's look at one more example. Here's example number 2. What volume of 1.65 molar copper 2 sulfate would be needed to prepare 500 mils of this more dilute concentration? It's asking me for a volume is the first thing I'm going to make note of. Is it asking me for initial or final volume? Well, what volume is needed to prepare a greater volume? Remember, the second volume will always be greater, and the initial concentration will always be greater. So here we're asking for initial volume. And this is a pretty common problem. How much of that stock solution do I need? The initial molarity of stock solution is 1.65 molar. The higher concentration is always the initial concentration. The final concentration that I want to make is 0.0825 molar, and the final volume is 500 milliliters. Now, just to make a point, I'm going to go ahead and put this number in liters. And if I had kept it in milliliters, then my final answer when I do the calculation would have come out in milliliters. Keeping it in liters, or converting it to liters, is going to give me a final answer in liters. And again, the formula that I introduced is MIVI equals MFVF. Let's go ahead and rearrange that to solve for VI, which is the unknown quantity in this case. Divide both sides by MI, and you see that we have this formula, MFVF over MI. I go ahead and plug the numbers in. MFVF is 0.0825 multiplied by 0.5 liters. Then I'm going to divide by MI, which is 1.65, and I'm going to get an answer in liters. Now, I could report that answer in liters, or I could report that answer in milliliters. However, in both cases, it looks like I should be 3 significant figures, and if I had kept my volume in milliliters here and typed in 500, then I would have gotten this final answer of 25 milliliters instead of this one. But either one of those approaches works. So let's talk for a minute about what this process actually looks like in the lab. You'll see in that last problem we needed 25 mils of the stock solution, and that's what's depicted here. This is the stock solution in something called a volumetric flask, and here a volumetric pipette is being used to obtain exactly 25 mils of solution. That is put into a volumetric flask, which is exactly 500 mils, the final volume of solution we're trying to make, and then we add water until we get to that final mark. So those are the steps that are involved in preparing a dilute solution for more concentrated stock solution. And this instrument is called a volumetric flask, and it only has one mark on it in this narrow part of the glassware so that you can get a very precise final volume. And of course, in the lab, we would ideally practice making some solutions, but we certainly want to make sure that we understand the calculations and see if you can visualize the way we carry out a procedure like this in the lab. Let's go through 1 or 2 more practice problems and look at a couple of different types of situation we might encounter. Here's calculation number 3 that's in the notes, and you'll see it says calculate the amount of stock solution needed. That's asking for VI. This is a pretty common problem. How much of that stock solution do I need? Needed to prepare 400 mils. Again, that's the final volume. And even though that's only one significant figure, I'm going to assume that I would like to prepare exactly 400 milliliters. So really, an infinite number of significant figures is implied here. And I'd like the final molarity to be exactly 1.5 molar. That's the target molarity, as precisely as I can. The stock solution which is available, and remember the initial quantities here correspond to the stock, is 2.8 molar. That makes sense. The stock solution is always going to be a higher concentration than the dilute solution. Rearranging MiVi equals MFVF to solve for Mi, we have MFVF over Mi, and we'll go ahead and plug those numbers in now. The final molarity in the final volumes product, let's try turning on the calculator first. 1.5 multiplied by 400. And again, notice I've kept my volume in milliliters. That means I'm going to get an answer in milliliters when I divide by Mi. And here I have an initial volume needed of about 214 mils. Now, that's a reasonable number of significant figures to include, but it wouldn't necessarily be wrong to include even more significant figures here, simply because these are not measurements, these are an ideal precision that I'm shooting for. And so if you have a way of measuring exactly that volume, then great. But here I would keep at least as many significant figures as are indicated, and typically on a question on a worksheet I'll ask you to report a certain number of significant figures. But we want to be as precise as possible when we're preparing solutions, so we'll measure the required initial volume as precisely as we can. So here's example number 4. It says if 25 mils of water are added to 8 mils of 12 molar hydrochloric acid, what will be the new molarity? If we're solving for new molarity, that's final molarity that we're solving for. The initial molarity was 12 molar. The initial volume is given as 8 mils. And it says 25 mils of water are added. So does that mean our final volume is 25 mils? Careful. If I add 25 mils of water to 8 mils of solution, I'm going to have 33 mils of solution. So occasionally we have to be careful that the amount of water added, of course, is not the same thing as the final volume of solution. Now I'm going to solve for final molarity. That's MiVi divided by Vf, and I'll go ahead and plug those numbers in. Initial molarity is 12 molar, initial volume is 8. And again, notice that I'm using volumes in milliliters. That's okay, as long as I'm consistent. When I divide by the final volume, which is 33, not 25, I get a final molarity of 2.91 if I'm using 3 significant figures, or 2.9 molar if I'm restricted to just 2 significant figures. The final molarity here makes sense. It is more dilute than the initial concentration, and if I had used liters in each of these cases, then I would still get the same molarity. But you want to make sure you're consistent and don't use milliliters in one case and liters in another, because then of course those units would not cancel. Let me walk through one more calculation. Example number 5 here says a 2-liter container of 8 molar sulfuric acid must first be diluted to 1.2 molar. So we have an initial molarity of 8, and we have a final molarity that we're shooting for of 1.2. So the molarity is going to be reduced, of course. The initial volume is 2, and the final volume is what we're going to solve for. What's the final volume going to be? MiVi divided by Mf. 8 multiplied by 2 is 16, divided by 1.2, I get a final volume of 13.33. Notice since my initial volume was in liters, my final volume also will be in liters. The next question asks how much water needs to be added. Of course, if we started with a 2-liter container and we have a final volume of 13.3, then that means 11.3 liters must be added, since 13.3 minus 2 gives me how much water needs to be added to get to that final volume. So that wraps up our introduction to diluting solutions. As you're doing the calculations, I think it's going to be really helpful to think about this simple scenario that's in the picture. You start with some small volume of a very concentrated solution, depicted here by that darker color. You add water and you end up with a large volume of a very dilute solution. That final molarity is going to be a smaller number because, as that lighter color indicates, this is a lower concentration to begin with.